So as you can see, the title of my talk today is going to be Demystifying the Spectrum with Machine Learning for Beyond 5G. So at high level, we're going to see, we all know what the state of the spectrum is. So we're going to try to understand how do we make sense of the spectrum? What are the tools that might be required, especially keeping the push of Beyond 5G in mind, and how this added information or a comprehensive knowledge of the spectrum around us could enable us design better algorithms and solutions that maximize the utility of the scarce spectrum that we have. So let's jump right into it. So here's the agenda that we're going to talk about today. So first I'll go through some of the progresses and where Beyond 5G requirements are at this moment. Then we'll slowly transition into multitask learning for wireless, which could be one of the solutions that we could be deployed for understanding the spectrum at a much deeper level. I'll try to present some of the experiments and findings that we have recently acquired. I'll talk a little bit about model compression, which is going to be key if we actually want to deploy these kind of solutions on edge devices or computationally restricted devices, which might be a phone, which might be others at the edge of the network. And then finally, conclusion. Hopefully we can have discussions. So feel free to always maybe post questions in the Q&A and so on. All right, so jumping right into the perspective from 5G. So here is a quick snapshot of the radio access technologies and its evolution. So I have two sections in this. One is, as you can see, the Wi-Fi here, which has progressed from A, B, and G, and now it's up to Wi-Fi 6, which also allows us to use the 6 gigahertz band, which is going to be idle, which is already unlicensed actually in US and other places. Similarly, you can see the progression of how the 3GPP standards have progressed. I've just started the snapshot at LTE, but now it's at NRU, and there's already significant work that's happening, at least in the academic level, to push towards 6G. Now, interestingly, what you see in common is, so first of all, the physical layers and the MAC layer are converging in the sense that they started off very different. But now you can see things like OFDMA, multi-user MIMO, and many techniques kind of overlapping, at least at the physical layer, for even if these radio access technologies are different. Another interesting aspect that you can see even with 3GPP standards, there is an infusion of spectrum sharing. So earlier you had licensed band, you didn't really care about sharing a spectrum in unlicensed band, but even if you think about now LTE-U, LAA, or NRU, the whole goal is now to use this scarce spectrum that is unlicensed and try to share the spectrum with Wi-Fi. So in broad sense, what we're going to see in the future years is any spectrum that's available, licensed or unlicensed, you want to use it to its maximum efficiency, whether it's by spectrum sharing, changing your power levels and so on. And while doing this, if you have a good understanding of your spectrum, you will be able to maybe choose an appropriate power level, appropriate modulation schemes, or appropriate actionable items that you can change your front-end radio parameters to maximize the utility. But to know that, a simple energy detector might not give you enough information. And that's where understanding the spectrum becomes important. But this just gives you an idea of why we need to understand the spectrum and what the trend has been in the radio access technologies in the recent years. So again, to make the point of how spectrum is scarce, this is just a small map, and many of you might have already seen this if you're working in this line of work. This is FCC's frequency allocation, and you can see, especially in some of the lower in the sub 6 gigahertz band, how occupied it is and how busy it is. Now, there are two options you can think about now if as the use of wireless spectrum becomes increasingly congested or competingly required. You can either find the new spectrum, which is there's a lot of work being done at that domain. That's why terahertz and other spectrums where it's still unlicensed, there's no license and there's huge bandwidths available. But obviously the challenges along with it comes, right? So which is poor propagation, shorter distances compared to say sub 6 gigahertz spectrum. But that's definitely an option, and that's also an area where machine learning can help, but in a different way. The second option is, there's a lot of usage on these things are licensed or unlicensed, and there's a lot of usages, but it's still not topped up to the maximum, right? So you want to enable spectrum sharing in the most efficient manner so that whatever is available is used to maximize your spectrum utility. And that's again just making the point of why this is required, why we have already started thinking about this, but now how do we get closer and closer to knowing a comprehensive information about the spectrum in the most efficient manner. Okay, so what does demystify spectrum mean? Or what are we trying to do here, or what is the requirements in the coming years? So there are a few things you want to know about the spectrum. Very simple. Energy detection, right? Is it occupied? That's the simplest question you might ask yourself before you're trying to transmit. So it's occupied, and that's nothing new, and everybody wants to know that, and just a simple energy detector might help you. Now, here's one part of the challenge. Now, is it a communication device? Is it a radar, or is it some other emitter? And this is becoming more common, right? Before you had license band only for radars, and communication devices do not exist there. But if you think about the CBRS band recently, there's US Navy radars existing there. You can use the same band as a secondary user, and so on. So the fact that identifying the emitter or what kind of emitter is there, that added information will allow you to take an action of whether to use the spectrum or how to use the spectrum. The next part is what is the signal descriptors? We have seen a lot of work in modulation, classification, bandwidth, or protocol identification, but the underlying takeaway is that one of these information may not be enough. You want to gather as much information about the signal that you see. So again, that might help you identify whether it's an authorized user, not an authorized user. The signal shouldn't be there, so maybe you have to take some other actions of finding the signal and mitigating it. If it's an authorized user, if you're the secondary user, you want to keep quiet till the primary user. So the more information you know beyond just sensing the spectrum, it's going to be useful, and that's the only way we can maximize the usage of the spectrum. And in tactical domain, you can also think of this as, is it a friend or a foe? So if you think about the realm of RF fingerprinting that's coming into play, you want to fingerprint all your radio so that when you see these emissions, you can easily see, oh yeah, I know these are within my tagged radios. Whereas you see some other emissions, this is definitely not within our friendly forces, so it might be a foe. So there's that aspect to it also, and it may not be just tactical. So you think about secure networks, the same ideas come into play. So again, just from the spectrum point of view, can you identify if it's a friendly signal or a intruder, or is somebody else trying to access spectrum in an unauthorized manner? So then comes the big question: can we answer all these questions in an efficient manner? So probably, and we'll see, maybe there's a way to answer more than just one. Currently a lot of the work is, okay, I want to classify the modulation. How do I do it best? Now, can you do more than that using a single model is what we're driving towards. And just at the cue, so this is where the talk begins, right? So multitask learning has been utilized in different domains, including natural language processing to look at emotions and things like that. Now, can you use the same techniques now to build a single model that's small enough that can be compressed, where it can do multiple tasks? It classifies modulation, classifies protocol, maybe even classifies RF fingerprinting, and so on, even regression tasks, right? So that's what we're trying to capture here. Can all those be done using a single model, and can they be customized so that they can be lightweight enough to be deployed on an edge network? So this slide is pretty much trying to give you the history or the story behind AI. And this is a pretty classic diagram that you must have seen in different spaces. I've just started the inception of AI at where Frank Rosenblatt invented perceptron, but that's, maybe I'm a little biased towards the name of my lab. And obviously there has been work on AI before that, but assuming that's a start point, right? We have already seen 2 winters of AI, which means there was a hype in AI, and then the hype went down due to some obstacles that has faced during whether it's computation or it seemed unreasonable to continue in this path. And then there was another hike, and then there was another dip, right? But now, as we are getting close to 2020, there's a huge explosive growth in AI. The question is whether this explosive growth is the truth and it's positive, or is it still a hype, right? That's the big question at this point. And based on the information I have, or based on what I've seen in the market, I'm leaning towards that a lot of this is actually truth, right? Reasoning being, even if you pull up your Netflix, you pull up your Amazon, or you pull up any services that's suggesting things towards you, what is it running? It's learning or AI-based solutions, models that are taking inputs from you, which is your data set, and your choices that you make, and trying to update the model to give you better results. There's also phase recognition, and there are generative models that's trying to map one domain to the other. So there are many applications that have already been put into commercial use. So it's definitely not all hype. But the word of caution is, since AI has become the keyword here and the word that sells currently, there is a tendency to push AI into all the domains and to solve problems that may not be actually the core strength of AI, or may not, you may not require machine learning or AI to solve it, right? So that's where the danger is. But I'm optimistic at this point. But as time goes, obviously, as scientists, we will reevaluate and we'll see where we are, right? And I also wanted to state, machine learning is a subdivision of AI, or you can say it's a subset of AI in general, just to make that caveat point. But so overall, the takeaway is it seems reasonable and seems positive in terms of growth, but we'll find out what happens in the long run. But I'm giving this talk because I feel there's something at least positive, and there's something to look forward as a solution that AI provides. Now, why is, so we talked about two windows, but why is this particular search different from other times around? Right, so I'm showing you examples of different curves here. So you can see the data growth. It means how much your data that's being stored is growing. You can see the storage cost of data coming down. And then you can also see the processing power going up, right? So these are just different graphs showing that this might be what's feeding or what's led to the, again, AI coming out of its winter. So the main point, like I mentioned, is the computation, right? So computational resources have exploded or grown exponentially, and the use of GPUs and parallel processing has enabled us to actually deploy machine learning based solution much more adeptly. And that's one big reason why it seems to be different this time around. The computational power is there, and obviously as our needs increase, is going to, currently it seems promising. But at the same time, here's the word of caution from wireless point of view, right? Though computation is available for most applications, right? You can have your big servers, you can have your cloud, but think about wireless nodes. Think about your mobile devices. Think about your IoT devices. How many of them have a GPU on it yet? Currently, no, not much, right? So there's always still a constraint in terms of computational resources when it comes to wireless point of view. You might have an FPGA, those who know about FPGA, right? And the question is, can you deploy a machine learning model on FPGA? The quick answer is yes, but there are constraints related to it, right? So even though computation has caught up, and that's something that is different this time, and it seems promising, but there's a word of caution in terms of wireless. Now, similarly, the second part is digital data, right? Now, compared to 10, 20 years ago, where even if you have a lot of data, there's hardly anything digitized, right? But now everything is digitized, right? Your digital cameras, anything that's captured, any videos, tons of videos on YouTube, all these data sets that are available for computer vision. So there is a huge advantage now because everything is digitized. So it is stored in clouds, it's available, you can train your models, and you can create even more digital data, and that's just growing, right? So that's going to be another advantage for machine learning. But again, thinking of digital data in terms of RF applications or wireless applications, it is still in its infancy. I don't want to say there aren't any. There are. It is becoming more. It's increasing more and more. But at the same time, it is nowhere close to say ImageNet or the data sets used for computer vision or other programs, NLP. It's nowhere close to that, right? And these are not just cautions, but also pointers to you guys saying, we are open to contributions in these fields, right? Something unique data set that you create, a comprehensive data set that you create that becomes the state of the art for everyone to evaluate on, or solving this edge problem or implementing these machine learning solutions for edge might be your opportunity, might be a research topic for you guys, right? So
So there are positives, there are negatives, but I wanted to bring this into context of wireless communication or RF domain because that's where my talk is going to be about. So, and with most of the slides, I will have at the end some of the sources and suggested reads for that, which will be a combination of several of my papers, but also other papers that are well known, right, and are pioneers in the field. So, for example, this is the overview. I would say this is a very limited overview of machine learning, right? It's broadly classified into supervised learning, unsupervised learning, and reinforcement learning. And personally, reinforcement learning, I think, is almost a completely another field and different from supervised learning and supervised learning. But according to tradition, it's still combined under machine learning. Right. For reinforcement learning, I would suggest reading Sutton's book, and for the deep learning or supervised learning, Ian Goodfellow's book referred here. Deep learning is really good. From this particular picture and the perspective of machine learning in wireless, we have published a paper that's pretty popular now, machine learning for wireless communication and Internet of Things. You can access that. It's also put up in archive to get an understanding of how these things can be applied to machine learning, right? And similarly, there's another paper that you can look at, which is applying machine learning to UAV systems that I talked about earlier. Uh, so dividing these into three broad categories, right? What I'm going to focus on and what the shade in gray shows is I'm going to focus mostly on supervised learning and reinforcement learning. Now, when you think about supervised learning, right, several of the applications for supervised learning include, RF signal classification, modulation classification. Now, implementing different signal detection techniques within MIMO to improve the MIMO system, signal recovery, error rate, error correction. So these are all areas where good, machine learning could actually help or improve performances. Similarly, in reinforcement learning, we have a problem in wireless domain or in RF domain. It has been applied to dynamic spectrum access, intelligent power control. How do I control my power so that I'm not causing interference to others, but I'm maximizing the network's throughput. Routing problems, so you're choosing which node to route to give you some objective gain. Cognitive radio, as being the secondary user, how do I intelligently access the spectrum as compared to the primary user? And obviously, overall, just radio resources allocation. This might be a multi-objective or multiple resource allocation problem, which means you have to choose between frequency, power, modulation, etc., etc., etc. Right. So many decision-making problems, learning from the environment, really fits into the domain of reinforcement learning. So this is just an overview of just high level machine learning and how these things are actually applied today for different wireless communication problems. And some of these, like I said, supervised learning and reinforcement learning, we'll be discussing a little more details to give you guys motivation of how you guys can apply this to research that you might be interested in.
Right. So now, since we have seen a snapshot of the different machine learning techniques, let's bring in the focus of supervised learning and its application to the RF signal classification domain. So broadly, if you look at the works, right, before machine learning was used, this is probably the trend that you see, and starting with the traditional approaches. Where machine learning was not exactly used, but there were feature-based approaches, maximum likelihood-based approaches, which were used to, say, classify modulation and so on. Then, when machine learning started creeping in, we saw that we could use techniques to first create features. This may not be raw IQ, but you take the IQ, you create time frequency transforms, or other features that you think that will be helpful in classifying the signal, and then feed the neural networks with these features as input, and then that helps you to classify. The next generation was almost forget about these handcrafted features. So these are expert features that you had to create, which is great. If you know exactly these features will allow you to classify it will help in a great deal. But they weren't generalizing as much, and also we were probably missing out on implicit features that are not specifically engineered to become the feature set. So what the next generation of classification systems did is took raw IQ, which is still done today. Like take raw IQ, feed it into CNNs or other neural networks and see how the classification does. And there was really good results with those. And we do some of the survey in these papers here. Now, once we have found out that using the raw IQ signals are giving really good classification performance, then the question is, okay, I classified my modulation, but that may not be enough. I need to classify whether what kind of signal it is. Pretty much going back to the previous slide that we saw, where we need to know multiple information. So now what we're doing in our lab, and we think this might be a good approach to answer multiple problems or multiple tasks in the same model, is can you design a single model that is able to extract these implicit features from IQ and give you multiple or answer multiple tasks, which would be modulation classification, signal identification, so it'll be able to tell you whether it was a LTE or a Wi-Fi signal or even a radar, and then what modulation it was. So more information, more actionable information that you have to take appropriate actions. So that's what we're going to see in the rest of the talk, how a single model could be used to extract more information about the spectrum and about who is occupying the spectrum at that moment. All right, so now moving on to the motivation of why this was required, right? So think about the state of the art that we just talked. Mostly people consider only a single task. And then even when they consider a single task, they might use architectures that are already used in computer vision, which means really cumbersome architectures, which may not be enough if you are looking to solve a specific problem. So if you have 10 signals to classify, 20 signals to classify, is an AlexNet required to classify the signal? Can something that is handcrafted be small enough, give you high accuracy, good generalization, and still be able to provide performance that you can within a small architecture that you can deploy at the edge? And the third is, as we start seeing more of these access technologies, whether it's radar or communication systems coexisting the same spectrum, the trend has been, okay, this paper is going to classify communication signals. This paper is going to classify radar signals separately. Now, we'll have to consider all the signals together. Now, there's always going to be new signals. That's a challenge, but we have to start considering all possible signals that might exist in the spectrum. So, an example of that is the heterogeneous operation environment in which both radar and communication signal exist, right? I mentioned about this, the 3.5 gigahertz CBRS band. There is the incumbent US Navy radar emissions, and commercial cellular emissions are trying to use the same spectrum. That's the exact example that I said, where now if you need the information of who's actually accessing the spectrum beyond just spectrum sensing, you will have to classify it into, oh yeah, this was a radar signal versus this is a comm signal. Now, tactical application is another important area where you have multiple signals coexisting at the same time. You have to be able to classify them in as much information as possible. And then finally, again, stressing on the low swap requirement, low swap, size, weight, power, right? Even this conference itself is trying to see how does autonomy enable to be more energy efficient and more green in that way. So if you have to deploy this on low power devices at the edge, your size of the models and the computation from the model should be low. So how do you minimize the size? So all in all, right, we want to propose a lightweight multitask learning architecture to address all of the above challenges and state-of-the-art problems that we have discussed here. Right. So now to further solidify the requirement for a multitask learning model, let me give you some examples here, right? So if you think about 802.11a OFDM waveform, so you can say it's an 802.11a Wi-Fi signal, but you still need to say whether it's a PPSK, QPSK, or QAM, right? So you have to identify it's a Wi-Fi, but also classify its modulation. And you can think about other parameters that might be required. Similarly, satellite signals or other signals use these exact same modulations. So just by classifying modulation, you may not be able to distinguish between the kind of protocols that you are seeing in the spectrum. Similarly, radar signals, where if it's airborne detection radar or ground radar, any kind of radar. So they usually, they all adopt pulse continuous wave PCW modulations, but they probably differ in transmission parameters, whether it's pulse repetition rate, pulse width, carrier frequency, and so on. So there, what you would have to do is classify them based on these changes and say, okay, yeah, this is this particular radar, because that again gives not only us more chance to use the spectrum, but also gives us an insight on what kind of systems are active in a special kind of, or in the spectrum of interest. Now, again, underlining the whole concept and requirement for this, it's not merely enough to identify modulation formats. We have to go beyond that and try to do, identify as much as possible from the signal. In this particular work, we have looked at 2 tasks, but you can easily see how this can be expanded to tasks beyond that, and that's going to be part of our future work. All right. Now, to take an example of how we can use multitask learning, a recent paper that was published as part of and presented at ICC in June, you can see here's an example. So if you look in literature, there are multiple ways you can use multitask learning, and hard parameter sharing is one way of doing that. Now, in this diagram that you can see a shared layer, and then you have a task-specific layers. You can almost at high level think of it as a shared layer learning feature representations that are shared between these tasks, and the specific layers trying to learn feature representations that are specific to those tasks. Now, what are the advantages of using this multitask learning? So inductive knowledge transfer, is used, which improves the generalization implicitly. You can also think about this as these specific tasks are also competing among themselves to try to improve them, but it's not being biased to a single task. So if you look at the loss function at the end, at the bottom there, it's a weighted loss function, right? So you have a weight for the first task, which could be modulation classification. Then you have a weight for signal classification task. And the goal of the entire model is to minimize the sum of those weighted loss function. So what's happening is they're implicitly competing, but trying to find out the generalized features that's going to help both. So if you compare it to a single task architecture, the hard parameter sharing significantly reduces the risk of overfitting. Other advantages are it improves learning efficiency. It takes advantage of mutual relationship. It means if the tasks are comparatively and they have similar features that could be extracted to do the task, that could be beneficial to the overall model. And this is an example of how we implemented our multitask architectures for this particular paper. So we saw how we set up a multitask architecture. Now we'll discuss about some of the experiments and findings based on that architecture. So as you can imagine, like any machine learning tasks, we need data sets. We need to create data sets that might not exist, or find a data set that's openly available. And for evaluation, you want to go stepwise. First you want to create a really dense enough data set that has all the dynamic requirements, and slowly add these dynamic natures to it, which is first you want to try out just adding noise, then you want to add dynamic characteristics like Doppler effects and everything to it. And then finally, and more importantly, you have to also test all this by transmitting this over the air and make sure your data set generalizes even to those scenarios and not just to in-lab cabled scenario. And that's what we're going to be seeing in this section, where what data set was generated, how was it used, what kind of results did we see from our fine-tuned models, and how did it look when we moved on to an over-the-air evaluation. So this is the data set. Now the good thing is, along with the paper, if you look at that link, this data set is available. So I'm not going to go through all the features. You can see the dynamic parameters. All that was generated in GNU Radio. And then you can see the different modulation classes, signal classes, and what application they are for, whether it's communication and radar. So this entire data set is available based, in the paper that we have presented and that Git repo for non-commercial use. And you can go in, you can play with it, you can try to set up your own classifiers. And the good thing is, now the biggest challenge we faced while we started looking at multitask learning architectures there weren't any open data sets that had multiple labels, right? So we had to create our own. Now this particular task or this particular data set, you can use it for single task. It means if you want to just classify modulation, you can design it and classify it such. If you want to just classify signal classes, you can do that. But if you want to design multitask architectures, you can do that too. I'm actually part of IEEE working group 19.8, we're trying to come up with standardizations for these data sets. And that's very important. We think that's going to be pretty important. And once we come up with the standardization for these data sets and people release these data sets as standard, it becomes much more useful for the community where, somebody wants to do single task, somebody wants this parameter, yes. But more information that you have about the type of signal collected, there might be multiple tasks or multiple models that can be run on the same data set, which seems to be a little difficult to do in the current state of the art. But the good thing is, here's the link. But if you don't get the link here, reach out to me later. I'll share the link with you, or take a look at a paper that also should have the pointer to the link if you want to use the data set. So I'm not going to go into details of hyperparameter tuning, but the big takeaway is, we had to tune the hyperparameter significantly to come up with the final model. But here are the interesting aspect. We know that the radio platforms are resource constrained, right? So we didn't start with, say, okay, let's start with a Google Net or AlexNet or any network that has already, CNN network that has already been used for, say, classifying computer vision task. Because that's impractical, it starts up huge. We don't need. So what we did is we started simple, put some layers, try out few kernels, and all these details are there in the paper of, what we tried, what we found. Sometimes a denser network really didn't help, so we didn't have to use it. Lighter network was faster in training, faster in inference, as you can imagine. So that is more than enough. So obviously, then this density directly affects the efficiency of classification and accuracy too. And we studied that and we present the results in the paper in much more elaborate manner. But we did all that and we came up with, okay, what's the reasonably sized model that we could use to get good performance, and let's run them using our data sets. But that's the high level picture of what we did for hyperparameter tuning. All right, now let's take a look at the performance of MTL model. So when you see RADCOM, it means radar communication. AWGN means it has uses only AWGN. So this has only noise and does not have the dynamic features that we have looked at. And this is at 10 dB of SNR. Pretty good performance. All the classifications are pretty high, close to 99-98% for modulation classification. Similarly, all the signals are also classified very well in the demultiplier. So now there's a single model that's putting out whether it's each signal for each IQ input it goes in. It says, okay, it's class A and this modulation A, and so on for each class. So there's not two separate models, single models doing this. We also did the same thing for dynamic data set. So while we were doing the AWGN, we used separate, we created our own data set, but we also, to make sure we have enough size of the data set, we used a data set that was available online too, and we were able to add noise. We couldn't add dynamic modulation parameter or dynamic parameters to it, so we stuck with just our data sets to do that, and that's what you're seeing here. We had 6 modulation, classification went very well. We had 8 different classes of signal, and their also classification went very well. So what you're seeing here is fine-tuned, really small compared to obviously the computer vision task models are doing extremely well with classification of multiple tasks or doing multiple tasks with a single. So in the last slide, we saw just for 10 dB, the 2 different data sets and 2 different tasks. We're just plotting all that here in this graph for varying SNR. And here are the big takeaways, right? So for AWGN channel with only noise, our classification accuracy was above 97%, even for 2 dB SNR. That's very low signal, low signal power. And for a dynamic data set, our modulation was 97, modulation classification was 97, signal classification about 90, for 2 dB SNR. So the experiments demonstrated that you can design these multitask learning models that can work on severely impaired waveforms. And you saw the waveforms if you look at the list of dynamically changing models that has Doppler effects and all the other effects included in it, and it's still able to perform pretty well. So that was a big takeaway from the paper that we published. All right, so here what we're seeing is a comparison with state of the art. So one of the challenges that we faced at that point was there were data sets, there were works that did a lot of modulation classification and signal classification using specific data sets, but none of the data sets could be used for multitask learning because they didn't have the labels of what kind of signal it was. If it had signal, it didn't have modulation, so we had to generate our own data set, right? So the comparison, apples to apples comparison, was very hard. But if you look at number of signals, in our case, it was 9 modulation and 11 signal classes. was pretty decent, pretty high. And if you look at the performances for 0 dB and 10 dB, our performance was consistently above 97% and 95% for modulation classification, 92% and 99% for signal classification, which when you compare against single task models that are available in literature, I provide citations there, but I could not list all the citations in this slide. If you go to our paper, all those numbers are corresponding to the citations in that paper. But the big takeaway here is when you look at each of these different work that looks at different modulations, many of them lower number of classes than ours, some of them with higher number of classes than ours, but maybe at a lower dB that they represent, higher dB that they represent. So overall, we were able to claim at least equal or greater classification accuracy, all that be in a different data set, right? So the point that I was making with dataset even earlier is if we had a generalized structure of having these data sets, we would be able to take one of these data sets and compare them. But we have the data set that we have released is capable of being used as a single task learning and multitask learning. And we have few data sets that we are prepping and preparing to release even in the future. But the bigger takeaway here from lessons learned is a single model is able to do both the task, which required separate models for the previous work, either at equal performance or even better performance. So those are good signs for us to pursue around this path and continue exploring multitask learning, whether it's adding tasks or adding data sets, larger number of data and modulation point. And that's exactly what we're doing in the next year and a half for our next program, right? So you might see more results from this, but at least it gives us a confidence that, multitask learning architectures work for our RF classification tasks. So now let's look at some of the over-the-air results. So this is just a snapshot of how we collected over-the-air data. So in GNU Radio, we implemented all these waveforms that we talked about. It's a custom waveform generator in GNU Radio. And then we transmit this using a USRP and TU10s. And then over the air it goes, and we receive it using just IQs, no processing, nothing at the stage, just IQs recorded at the receiver. And then we use that data to do our next set of experiments. So before describing through the results, I wanted to give you an idea of, again, so in simulation, it's easy to say, okay, this SNR, that SNR. But obviously, when it's over the air, it becomes a little more challenging. So what we use here is transmit gain. So here I have example of two radars, ground mapping radar and airborne ranging radar. And you can see the difference, what a 32 dB signal looks like and what a 0 dB signal looks like. And you can see 0 dB is almost non-existent, right? Just very less signal power, and that's what we're sending over the air. And in terms of results, the performance stayed pretty consistent. So we used transfer learning, we started with the model, we retrained it on this over the air data. And as you can see, the results were pretty good for 8 signal types, 6 modulation over the air. Our performance was for modulation classification, it was close to 90%, and for signal classification, it was well above 95% for all the transmit. Even for the lowest transmit gain, you see that the performance of the multitask learning model was pretty good. We are discussing some of these results in an upcoming journal paper, and hopefully that'll come out pretty soon. So a big takeaway is here, right? So multiple tasks. So I want to emphasize that this is just an example of we showed 2 tasks. It's easily expandable. So you can add tasks that you think are relevant for an application, whether it's commercial or tactical or any application, you can extend the task. It has shown pretty high sensitivity, which means even at low SNR, we were getting about 90% accuracy in classification, which is a good indication of, these ideas can be used, they are viable, and there is a lot of ground for doing research there. We did publish our open source data set to use for the community to use, try it out, make models that do even better, try out the ideas. And the good thing is you can use it for single task and multiple tasks. So feel free to use that or reach out to me if you cannot find it. And again, the last point is just mentioning what I said earlier, is that this is expandable. It doesn't have to be 2 tasks, 3 tasks, 4 tasks. That might be another study. Like if you add too many tasks, now things start negatively impacting the model. So we need to find, there might be a good area of research to say, how do you understand what's the limit of these multitask learning models? And there's some of the work we are doing back in our lab too. All right, so now we have seen, so I've showed the problem. One part of the problem was, yeah, we're just focusing on a single task, which might not be enough, because think about having 10, if you have 3-4 tasks and you have each model for the task, it becomes really tricky. And here's the other aspect. Regardless of whether we customize, we have a small model, we will have to rely on some model compression techniques to make it even smaller without losing its performance, so that you can put it on the edge device. And I want to give you a quick snapshot on that. A few slides on possible directions to take for that particular aspect. So when we develop these solutions for wireless applications, one thing we have to try to ask ourselves is, are we thinking about deployment during the design phase? So think about beyond 5G perspective, right? We have already talked about, we need to know, we have to have a better spectrum awareness at the edge. You can also think of some applications that might be secure authentication related and spectrum sharing, which we have already discussed. Now also think about the actual computing resources that are currently at the edge. It might be really resource limited, and they already have other computations to do. So if this has to be a practical deployment in the future, we have to keep the model small enough if you want to keep it at the edge. I'm not in any way saying that we won't have solutions that can go on a cloud and can use higher computation. Absolutely, we have to use those. But the ones which might need faster reaction time, need to be deployed at the edge, it becomes more and more important, especially thinking about the latency requirements for beyond 5G networks and so on. So what's a general trend, and this is for machine learning solutions in general, is also focusing on accuracy, but then you don't think about the model size. And again, the advantage there is you have cloud and you have a solid connection. You can use cloud computing and all the resources at your disposal to make this decision. And for those applications, it's all fine and good. But thinking about the goal of this particular conference, where you talk about sustainability and automation, it has multiple folds of implications, right? Reducing the power level, reducing the amount of energy used when it's deployed at the edge, making decision fast enough where it keeps up with the latency requirement of beyond 5G networks, all that comes into play. So it's always important to think, okay, where is my target deployment location of this? And can I go with a huge model, or do I have to stick with a small model? So then comes the question, how do we squeeze your neural networks? So at high level, it's pretty much, you have so many parameters, you have so many computations that are required. The large scale idea, or at a high level ideas, remove redundant ones, the ones that are not very significant, identify them, remove them from the network. There is your compressed model. So one specific example, and this can be done layer wise, channel wise on the whole network, is quantization. When you're training it, when you're designing it, you're looking at all the possible combinations and permutations, and you're optimizing it. You probably don't want to quantize it at that stage. But after you start seeing good performance, yeah, these models can work. You start looking at, can I reduce the precision bits that I'm using? So moving from a floating point 32-bit into a int 8. Right, and that saves some quantity of memory space and computation. So that's one example, quantization. But other examples, unstructured pruning, which is nothing but removing the insignificant weight. So you can use parameters like L2 values, L1 values, and see, okay, which are the parameters that might be contributing the least and does not change your accuracy. So prune those. Next one is structured pruning. So for structured pruning, you can think about removing your neurons, removing filters, removing redundant channels. So all these come into play if you want to reduce the size without affecting the accuracy. So here's the challenge. You want to preserve your performance, you want to preserve your accuracy. How much trade-off do you have? How much can you remove? And this becomes a process of training, testing, or in other words, squeezing, training, testing, squeezing, training, testing after you have initially started with a baseline model. And I think so this is going to become increasingly important for applications, especially for RF domain applications, where in future you could see things like similar things being deployed on your mobile device and other edge devices, IoT devices, and so on. So here is an example of the pipeline that you would use for compression and something that we used for our applications. So this is a simple example of how quantization is used for model compression. If you see, you can start from RF dataset. First, as everybody does, you partition a dataset for training, validation, and test. You train your model using floating point 32, do all the hyperparameter tuning, and then you have a fine-tuned model, which we saw results from. The next step for you is, okay, let's see if can I quantize this and see if it gives me reliable performance. So you do quantization, model quantization, and then you do quantization aware training. It means you quantize, you train, you see the results, you do model quantization aware training, then you do testing for inference, and then you have the compressed fine tuned model. So now you have a much smaller model than you started with, which was already customized to be small. Now you can deploy this on edge devices. So that should be our goal, and that's one possible way of looking at what the pipeline should be. Now you can replace that quantization aware training with any of the model compression techniques and even future model compression techniques that I described in the previous slide. But the idea is you start with a good model, you specifically design model for the application, and then go through the model compression techniques to deploy this on edge devices. So we have seen an example of. All right, so now let's take a quick look at how we used it, right? So in the particular paper referred below, we saw how SqueezeNet reduced the size of AlexNet by 50% without accuracy loss. Similarly, what we have seen in our work is our baseline MTL that are shown in this paper. We have already taken some of these compression techniques and reduced the size by 11, close to 12 times without any accuracy loss, right? So that's huge, especially thinking about resource-constrained applications. That might be a deciding factor whether it can go on a device or not. So yeah, just a takeaway to keep that in mind. Always for these applications, when required, when appropriate, saving energy, saving computational load, all these might become highly important and applicable. So now we have talked about techniques, compression, edge deployment, and how that might enable the 5G solutions in the future. Now let's look at the open challenges, right? So every time we design, we have X number of signals, we have classified, there's a growing number of signals. So think about how, if you have already deployed a model, do you have to retrain the whole model to add more signals? Perhaps yes, perhaps no. So think about research in the direction of few-shot learning that's already happening a lot in the computer vision domain. That's something we could adopt and say, okay, this is a new signal, let's add it to the model. Can we learn from few shots of that signal? The other one is signal separation. So as it becomes crowded, many of the assumption, and even in our work, the assumption is there's only one signal. So we might need signal separation techniques right at the front end to separate these signals when we are deploying this for an actual process. It could be as simple as filters, but what if there are overlapping signals that might exist? So another area of research, another area of opportunity. Flexibility in the model. So what do I mean by flexibility in the model? Can you reduce the number of classes, increase the number of classes? Can it be hardware agnostic, which is the next point, right? So that's another aspect. So there are hardware specific signatures they leave on the samples that it's collecting. If I train with hardware X, can I deploy that model without much training or without much retraining on a different hardware? If it's not, that's a big challenge, because you have a model. If you have to train it on each and every device or from the receive signal of each and every device, that becomes close to impossible. So testing this model to see if it's hardware agnostic, designing models that are inherently hardware agnostic might become important. And the last two points are related to dataset. More standardized dataset is required for RF research in ML to take place in a much more efficient and adept manner. And that's why I said, the working group, IEEE working group that I'm part of, is trying to look at coming up with a standard. This is what we would follow to create dataset, create these machine learning tools, and so on. And finally, the data sets which we create, we rely on software-defined radius, which is great. It's great to prove concepts. It's great to this one. But when it comes to deployment, we need tons of real-life data sets. And it's harder to generate, create, collect than, say, some other fields. So how do we bridge that gap? Can we have standardized real data set, means from LT TARs? We have been collecting that for our use, but I wouldn't say it's as comprehensive as we would like it to be. So there's a huge opportunity there in creating this wide range of real life data sets, not synthetic data sets generated from, say, software defined radio. So these are some of the challenges and all right. So I do have a single slide after this, but this, we have come to the conclusion of my talk today, and here are some of the key takeaways, right? So as we move on to next generation beyond 5G, 6G, the competition for the spectrum and the need to use spectrum more efficiently is going to become pretty drastically important. And that's where you need a comprehensive, actionable information about the spectrum around you. We have seen how a multitask architecture could be one direction that you can take in that to accomplish that. And we have seen how efficient expandable approaches would allow you to add more tasks to a single model and be able to understand the spectrum around you more comprehensively. There are definitely other approaches you can think about, even multitask architectures that are different architectures that could be explored. More importantly, we have already demonstrated high accuracy for both the dynamic environment and over-the-air evaluation, which is great and which is very important because evaluation is key, especially even if it's in a lab environment, an outdoor environment. Cables will give you significant results and good results, but over the air, it adds that extra randomness or unknown features into your signal. And if you're able to perform there, especially in multiple places over the air, it shows that the model is able to generalize well. So that's a key aspect of any research in this area. Another important part was the small footprint, right? So with the growth of IoT devices and other edge devices, it's going to become important that the models that we want to deploy for these applications are small, can be deployed for real-time applications. So model compression techniques that we discussed and even the future techniques that might come up is going to enable us to reduce the size of these models small enough where it can go on these devices and perform the tasks that we want to perform. And beyond all, I want to stress on the fact that there are so many open problems and challenges in this area to innovate, and I would welcome everyone listening to this who are interested in this area to join forces and bring in some and solve some of these fundamental problems that we have discussed in the previous slide. So, that kind of concludes most of my discussion here, but I will leave one more slide that just gives you a glimpse of other things that we do in our